Hello everyone, my name is Jagriti Sharma and I'm an educator on the Unacademy Plus platform. So let me tell you a little bit about the Plus platform. Guys, we are conducting live classes on the Plus platform, and you can actually go to the website, Unacademy website, and you can type my name Jagriti Sharma, and there you are going to be able to access a lot of recordings. Okay, so you'll be able to access a lot of recordings of the special classes, or basically the free classes that I have taken. Okay, so these special classes actually give you a feel of the Plus platform. So basically they are free live classes and they are very interactive. They're just like the normal classroom experience, because you can ask me questions whenever you have a doubt and I can clear it to you in between the session also. So basically you'll get a lot of recordings, and guys, there are a lot of other educators as well just like me who are teaching on the Unacademy Plus platform. So my focus is on the CSIR-NET exam. As you all know, what is a CSIR-NET exam? It is basically a government, it's a national exam, which is if you qualify JRF of the CSIR exam, then you will be eligible to get PhD fellowship, and if you qualify the LS, you will be able to get the lecturership. Alright, so I'm taking classes for the chemical sciences, and I'm helping you guys prepare for the CSIR-NET exam, and I have conducted some free courses as well. So in these free courses you will be able to see and you will be able to access the free video courses, and guys, you must see these courses because you'll be able to see that what the Unacademy platform is able to provide you. And this is my profile. If you download the Unacademy Learner app, then this will be the preview of my profile over there, and over here you can actually follow me. There will be a follow button over here in green, and you will be able to follow me to get regular updates on the special classes. These are the special classes, are our free classes, and they'll give you a feel for the Plus platform exactly, and you can get all the updates from me from all the classes, the free video courses, the special classes, and so on. And guys, yes, this is my code Jagriti S, and guys, there are some subscription packages also. There are the 1 month subscription, 3 month subscription, 6 month subscription, 12 month and 24 month subscription. So if you want to take any of these subscription packages for accessing all the live classes, for attending all the live classes, as well as the doubt session, as well as the weekly quiz, okay, so you can take one of these packages, and if you are using my code, then you will get a 10% discount on any of the package which you are selecting. Alright, okay, so basically in today's class I'm going to tell you a little bit about the spectroscopy. We are going to study the spectroscopy in very much detail, but here I'm going to give you a very brief introduction of the spectroscopy. So first of all, let us understand the terms which are used in the whenever we are discussing spectroscopy. Okay, so the first thing that we want to know is the frequency. Okay, so what is frequency? The number of waves passing through a point in 1 second. Okay, so that's a very basic definition, guys. We all know what is frequency, and it is represented by nu, and the unit of frequency is cycles per second. It can also be written as CPS, or it is hertz, which is Hz, and 1 hertz is equals to 1 cycle per second, or actually we also write hertz as a second inverse also. Okay, now we talk about wavelength. Okay, so guys, we also know what is wavelength. It is a distance between two consecutive crests and troughs, and it is represented by lambda. So what are crests and troughs? So if we this is the most basic representation of a wave like this. Okay, so if you are representing a wave like this, the upper portion over here is what we call the crest. Okay, so this one over here is our crest, and this portion below is called our trough. Alright, so the crest and the trough make one wave. So if we are counting from here, if we start from here, then this will be our one complete wave. This one is going to be our one complete wave, and the distance is called our wavelength. Okay, and that is called lambda. Alright, So there are various units of wavelength. The most frequently used are angstrom, and 1 angstrom is equals to 10 raised to minus 10 meter. Then we have nanometer, which is 1 nanometer is equals to 10 raised to minus 9 meter. And then we also have the other most frequently used unit, which is the wave number. Alright guys, so definitely we use frequency and wavelength, but we also very frequently talk about the wave number. So a wave number is the number of waves passing through per unit length. Alright, so if we want to quantify the wave number, then we are going to represent it as nu bar, which is equals to 1 upon lambda. So this is just the opposite of wavelength, which is actually the number of waves passing through per unit length. Alright, and the unit which is definitely inverse of the wavelength. So if you are taking the wavelength in centimeter, it must be centimeter inverse or meter inverse. Alright, then we have one more relation regarding this, that the speed of light, which is equals to frequency into wavelength, can be written like this. And if we want to let's say represent, the energy value, or if we want to make some important equations out of these variables, then we should remember some of these equations like this. So basically I have noted down the important equations for you guys. So if we if you want to calculate the energy of a photon, so basically guys, we know that what is if we are talking about photons, so basically we can say that the light is actually it is actually consisting of quantized packets of light, and these quantized packets of lights are called photons. So we will definitely want to calculate the energy which is involved in the photon. So how do we calculate the energy? This is our basic formula. E is equals to h nu, where h is the Planck's constant and nu is definitely our frequency. And this equation can also be written like this: E is equals to hc by lambda. We just saw in the previous equation c is equals to lambda into frequency. Alright, now if we want to write it like this, it can also be represented in this way: the frequency is equals to speed upon wavelength. Yes, so that is what I have done over here. I have replaced the value of nu by c by lambda. So this is one more way of writing the same equation, E is equals to h nu, as E is equals to hc by lambda. Alright, now we had also seen that the wave number, which is nu bar, is equals to 1 upon lambda. We had also seen that. So guys, we can very easily write this formula in this way also: E is equals to hc nu bar, okay, where nu bar is our wave number. Alright, there's one more thing which we usually want to remember, that is, if we are calculating the energy of a photon, which is a single photon, then it is E is equals to h nu. However, if we are calculating the energy for 1 mole of photons, which means we know 1 mole is Avogadro number, okay. So if we want to calculate the energy of 1 mole of photons, then we must multiply h nu with n, which is our Avogadro number. So definitely guys, we know what is n. N is equals to 6.023 into 10 raised to 23. Alright, so these many this is just the number, the Avogadro number. So if we are talking about Avogadro number of photons, then we are going to multiply Avogadro number with the h nu value. Okay, so this can again be written like this: n h nu. Also it can be written like this: n h c by lambda, replacing the value of nu. Also it can be written like this: n h c nu bar, where nu bar is 1 upon lambda. Alright, I hope that these equations are very clear for you, and I hope that you will try to convert them by yourself as well. So the type of question that can be asked from these equations, from these important equations, are like this: that the first question can be convert lambda, which is equals to 10 raised to 4 nanometer, into corresponding wave number. So they are basically asking you wave number from the wavelength. So this is something very easy. Also find the energy of photon. Now they're also telling you to find the energy of the photon as well. So the wave number, which is represented by nu bar, is equals to 1 upon lambda, and it can be also written like this. See, we had nanometer, we had the wavelength in nanometer. So what we want to do is we want to convert the nanometer either into meter or into centimeter. So if we convert it into centimeter, 1 nanometer is equals to 10 raised to minus 7 centimeter, and that is what I have written over here. And if we calculate this, then the value would be 10 raised to 3 centimeter inverse, which is basically 1000 centimeter inverse. So basically our wave number for the wavelength 10 raised to 4 nanometer is equals to 1000 centimeter inverse. Okay. Then we also can find out the energy value for this wavelength, which is going to be hc nu bar. See, we can also calculate from this formula hc nu bar, or we can also calculate from this formula hc by lambda, whichever you feel good. Alright, so I have calculated it from this formula. H is Planck's constant, 6.6 into 10 raised to minus 34 joule second. I have taken the approximate value, which makes the calculation easier, multiplied by 3 into 10 raised to 8, which is the speed of light, approximate again, meter per second. Then we have the wavelength lambda, which was 10 raised to 4 nanometer, and nanometer is 10 raised to minus 9 meter. So basically I have kept the value into meters because I want to cancel it out from the speed, right, like this. So meter is going to cancel out, and second inverse is going to cancel out with second, and only joule is going to remain, which corresponds to the value of energy. So our final energy value is 19.8 into 10 raised to minus 21 joule. Okay. So these are this is one of the type of question that can be asked, by if we consider these equations. Okay. Then what we have is, one simple thing that we always have to remember whenever we are talking about any spectroscopy, any study of the substances. We have to remember the electromagnetic spectrum a little bit, if not completely. Then we have to have an idea of which let's say spectrum is having what wavelength, or at least what we can remember is we can remember the basic values, or let's say the basic areas that we are concerned with. So basically whenever we are studying the spectroscopy, whenever we are studying any kind of spectroscopy, the most importantly, or let's say the most frequently studied, are the UV visible. Then we have the IR spectroscopy, then we have NMR spectroscopy, and so on. So basically in the UV, if we talk about the UV region, it is covering 190 to 380 nanometer. Okay. Then we can also talk about the visible region. It is falling under 380 to 800 nanometer. So basically in some of the textbooks it is written 380 to 750. In some of the textbooks it is written 400 to 800. So basically it is stretching around 800, stretching till 800 nanometer. And definitely when we are talking about the infrared, if we are talking about the infrared, it is more it cannot be it should not be taken into nanometer, because it will be very, very small. It will come into a very decimal value. So what we can do is we rather take it into microns, which is 10 raised to minus 6. Okay, so it is 2.5 to 15 microns, the infrared region. So here we can see our the electromagnetic spectrum that we have. If we start from the cosmic rays, so these here will be our cosmic rays over here. Then we have gamma rays from 10 raised to minus 14 to 10 raised to minus 12 meter. So we are actually taking the scale into meter. Then we have 10 raised to minus 12 to 10 raised to minus 10. We have X rays. Then we have minus 10 raised to minus 10 to 10 raised to minus 8, the ultraviolet rays. Okay, so basically they have taken the values into meter also. And the visible region is a very small region, so we can just for easier understanding, we can just take it into nanometer, and just like we have studied 380 to 800 nanometer. So if we start it from here, 380 to again for 800 nanometer over here. So this will be our ultraviolet, or let's say this will be our visible region. Okay, then again we move forward for the infrared region, which is 10 raised to minus 6 to 10 raised to minus 4 meter again. And again, if we move further, we are going to get the greater wavelength and lesser frequency microwaves, 10 raised to minus 2 meter, 1 meter, 10 raised to 2 meter, and so on. So see guys, what is happening if we are moving from left to right, then the frequency is basically decreasing and the wavelength lambda is increasing. So this is the whole electromagnetic spectrum that we have to have an idea, a very little idea. This is a very basic idea, and this idea also includes what we are going to remember about the the regions, the UV region, the visible region, and the IR region as well. Okay, then let me also tell you a little bit about the absorption and the emission spectrum, guys. So basically I hope that you have a little idea about it, that basically there are two type of electromagnetic spectrums that we can have, the absorption spectrum and the emission spectrum. Okay, so what are the absorption and the emission spectrum, and what are the differences in between them? We are going to see that very briefly. See, all the photons which are falling on a molecule are not absorbed by it. Okay, so basically all the photons which fall on a molecule are not absorbed by it, because the energy levels, the energy states are quantized. Because of quantization of energy states, only some energy is absorbed and the rest is transmitted. Okay, so what can we do if we want to study a molecule? Either we can study the absorption energy or absorption frequency or wavelength, or we can study the transmitted frequency or wavelength. So a spectrometer basically records the energy absorbed, or let's say the energy transmitted as their wavelength or frequency. So basically a spectrometer is going to give you a graph like this. So basically if we want to study the absorption or transmission of a wavelength, we have to study the intensity. Okay, so the intensity of light which is absorbed or transmitted is plotted against the y-axis, and the wavelength or the frequency can be plotted against the x-axis. So basically this is a typical graph which can be plotted for a spectrometer, just like the UV spectrometer and so on. So basically guys, the UV visible spectroscopy, the IR spectroscopy, the NMR spectroscopy are all absorption spectroscopy. So basically they are all studying the energy absorbed by the molecules. Alright, so the peaks which they are going to give are definitely going to be the peaks which depict the highest absorption. So guys, in absorption spectra, a graph like this, the intensity of absorption is noted down, let's say in the UV visible. Okay, and the peaks which we are obtaining are actually giving you the wavelength over here at which the absorption is maximum. So intensity of maximum absorption is given at a particular wavelength like this. Alright, okay. So now a little bit also about the emission spectrum, guys. So definitely some light, see, if we are talking about the absorption spectrum, basically what we did was, we just excited the, we just let the molecule absorb some light, and we measured the absorption wavelength or frequency. Similarly, what can happen is a molecule can be made to emit some frequency or wavelength, and that emitted frequency or wavelength can be it can be recorded. So that is what happens in the atomic emission spectroscopy. What we are doing actually is the molecule or the atoms, they are excited to a higher energy state by heating, and they also, whenever they fall back to the ground state, they emit some energy, and that emitted energy is recorded. Okay, so basically if we try to understand and if we try to see the pattern, the emission spectra is going to look something like this, in which the molecule, or let's say the atom, whichever species we are taking, they are going to give you the lines of the emitted colors. Basically these are the wavelengths. Okay, so these are the wavelengths, and that is why they are having different colors. So basically the excited molecule, when they fall back to the ground state, they are going to emit the specific wavelength of energy, which can be recorded like this. And if you are talking about the absorption spectrum, it is going to be something like this, in which see, we just talked about that the energy states are quantized, so they are not going to absorb all the energy. So they are only, the molecule or the atom, they are only going to absorb some portion of the whole electromagnetic spectrum, and whenever they are absorbing the wavelength, we are going to get the dark lines for the particular wavelengths. Alright, so we are going to get the dark lines for the absorption spectrum. And there is one more thing, guys. If we talk about a particular let's say a particular atom, let's say we have sodium. If we are talking about a particular atom, it is going to give the same emission, the lines which are over here. See, we have two lines for sodium, right? So basically the lines which are seen for sodium, the same lines are going to be present in the emission spectrum of sodium, and the same lines will be the same lines will be absent from the absorption spectrum of sodium as well. So a particular atom or a species is going to always give you a particular line or wavelength at which it is absorbing, or definitely at which it is emitting. Alright guys, so I hope that you were clear on the basics, and definitely we are going to see more videos. We are going to have a lot of more content coming up on the spectroscopy. And guys, if you like the video, then please like it, share it, and also subscribe for more upcoming videos like this. Thank you so much for watching.